We're gonna make sure that people at home can hear this. So welcome back, some of you, and welcome to this room for the others. Welcome to our second talk on the CoreOS track. Just as a quick reminder, we're gonna have a talk, then Q&A. Please wait for me to give you the microphone so the wonderful folks at home can hear your questions. And without further ado.
Hi. Oh, wow. This works. That's cool. Hi, I'm Michael. And today I'm going to be talking about how at Improbable we use etcd to drive dynamic configuration of our services using flagz, and how we use it to experiment with our stack. Okay, so a little bit about myself maybe. I'm a distributed systems software engineer. I used to work at Google. I was a site reliability engineer. I started working on Google Talk and Google Hangouts video, and then I moved to be the tech lead of the Google Compute Engine SRE. And about 1.5 years ago, I moved to Improbable, a startup in London that builds distributed real-time simulation platforms. And I'm a head of infrastructure at Improbable. This means that my primary job is to work towards a better platform API that our users consume, build cluster management tools that allow us to host the users' simulations, and also write memes. So this presentation is going to be full of memes, so I hope you guys at least enjoyed this part. So what is Spatial OS? Like a little bit of background of why we actually did all this. It all stems from what our company is developing. We are building a distributed operating system. This is a very nice marketing term that our marketing department really likes. But what really it is a platform for real-time spatial-based simulation. So you can think about it as like an app engine for doing simulations of spatial problems. Spatial problems such as city simulations or simulate like massive MMOs. Like basically the applications of the stack are quite varied, but the core tech itself exploits this one single concept of spatially placed entities that have the states simulated by arbitrary workers. So this all sounds like nice marketing fluff, but how does it actually look like? So Spatial OS is a given user's deployment consists of two main components. The runtime, which is written in Java and some bits of Scala. Each of those runtime nodes stores the state of the simulation and also performs stateful load balancing of the workers that actually perform the simulations of entities in our space. Those workers can be arbitrary programs that can link against our C++ library, such as a Unity game engine or Unreal game engine or Vism transport simulator, like pretty much whatever can load up a set of entities, do some simulation, and channel it back up into the simulation runtime. So the Spatial OS deployment actually is a little mini cluster in itself. Like the runtime basically forms a cluster of itself, but that Spatial OS deployment also lives in what we call the deployment cluster. And a deployment cluster is a multi-tenant environment that hosts the simulation deployments. This deployment cluster can host simulations of different customers. This can be a single deployment cluster can host a MMO, MMO for like a game, or it can contain short-lived simulations of the traffic infrastructure of London, for example. And this single deployment cluster is the bit that the infrastructure team runs and is providing third-party tools for the simulation deployment, Spatial OS deployments to run in. On top of that, we also have So as such, since you could think about the deployment cluster as the hosting environment for simulations, we also have separate platform clusters that host the API services that allow the users to interact with our platform. These include the API server, which is mostly written in gRPC and Go, an auth server that we build up so that our customers can have ACL access to only their stuff, and a proxy server that allows users to access certain endpoints of the simulation from outside of the internet. Now, the reason why we're talking about this and the reason why we're so excited about being here at CoreFest is because literally all of this runs on CoreOS. Each of those deployment clusters and the platform clusters is a separate etcd and CoreOS clusters in itself. We use Fleet for management of the deployment nodes, and we also use Fleet for the management of our API servers. We also leverage etcd for pretty much everything you could for the purposes of bootstrapping a cluster. We not only use it as a backend for Fleet, we also use it as a service discovery mechanism for based on SkyDNS, and we also use it as a way of configuring our Prometheus monitoring stack. So let me talk a little bit about the Spatial OS deployments, and I'll give you a little bit of background of why we're actually doing this crazy stuff that is going to follow. Well, Spatial OS deployments are not your usual web front-end jobs. They are not stateful. They're not stateless. They're very much stateful. They can be either short-lived, such as when the spatial runtime engineering team wants to conduct experiments of the new code base, they want to try it out and see how stuff works. They will spin up a new Spatial OS deployment and test against it. Users, when they want to develop remotely and they want to hook up the workers that they're developing on the local machine to a runtime that runs in the cloud, they will spin up a single instance of a runtime and connect to it. And that means that not only do we have this combination of short-lived and long-lived jobs, but also the jobs vary massively between one machine and hundreds of machines that allow you to, for example, launch a production-scale MMO. We also run about 200 spatial deployments, such combinations of runtime nodes and worker nodes a day. So this whole system needs to be very dynamic. The jobs themselves are named by the users because the users control how they want to deploy on a stack. They also dynamically configure them because, well, it is a very complex system and they want to be able to tweak it in runtime. And again, as I said before, the deployments are stateful and they scale themselves. The actual simulation runtime makes decisions when it needs an additional machine to perform the simulation. It will ask the deployment cluster's infrastructure to provide it with an additional node and then scale it up. So when I mentioned the dynamic configuration, like here's a couple of examples of why our users and our own developers in the company find it very useful. So for example, you're an engineer in the runtime team, and you want to experiment with the new load balancing policy. Now, you can dynamically change a value of the threshold at which workers are being added or removed into the system. You can, for example, on a live game or a live simulation of the city, enable or disable the experimental behavior of a runtime. So for example, you can say, I would like the new spatial query path to be enabled for like 20% of the queries and then compare them on graphs and see how they behave versus the old implementation. And also the users of our platform, the developers of the simulations themselves, can alter the behavior of the simulation in real time. So for example, they will be able to tweak how fast the trees grow in the simulation. We've had tuning problems all the time when, for example, if the trees grew too aggressively, basically the whole planet will be a massive jungle. So clearly, you don't want to do what people usually do. So have you tried turning it off and on again? Like, if you have a massive world consisting of 200 machines or 300 machines, you don't want to like spend your time waiting for all of them to cycle through and come up again. So that's why, and additionally, the other aspect of this is that our runtime is based on the JVM, and unfortunately, the JVM configuration mechanisms are kind of stuck in the 90s. So you have either a choice of like, I have system properties, great, or I have a massive XML file, great, or a combination of both, and I never know what to do with them. So we took a cue from the Google book. So since I used to work at Google, like that kind of inspired me as to how to bring the JVM configuration to the new millennium. And we decided to go with flagz. So flagz basically being parameters that you can specify on the command line and influence how your job behaves. No system properties, no XML files, just a single configuration, -- something something equals blah. And we've been running this for about a year now, and this is what our engineers and the runtime engineering team say about the whole thing. They hate it and they love it. The fact that they can specify configuration pretty much anywhere in the code base means that this is what -- help looks like. Now, what is flagz for Scala and Java? So, first of all, we wanted to get rid of the whole concept of I have a config class or I have an XML file that I need to pass around through my code base and basically destroy all of my constructors and stuff like that, and I have to always remember to inject it and blah, blah, blah. We didn't want to do that. We took a cue from arg4j, which basically allows you to annotate a field in a class with a certain annotation saying, hey, this static field is now a flag, and allow it to be changed. However, instead of taking the arg4j approach where you had to explicitly define all your flags in a single class, we allow you to specify it anywhere in your code base. So you can specify the flags related to your RPC parameters with the RPC parameters code, the things related to your monitoring with your monitoring code, and basically keep the configuration as close to the code as possible. Now, those parameters can be overridden on the command line, which is really good when you want to run stuff in a Dockerized container. Like, you don't have to think about, oh, how do I actually put this into a file and then I put it into the Docker container and like, oh my God. But also, we enable you to change those variables in a dynamic fashion. Those things are just variables in your code, so why not be able to tweak them when the server is running, right? And we hooked up that bit to etcd, which I'm going to talk about later on. Now, the whole flagz library allows you to specify either simple types, such as like integers, doubles, strings, like basically the standard stuff, but also generic containers, such as you can have a map of a string to a double, or a map between an integer and a string, whatever you want. And also, it's very extensible, so you could easily define your own flag by just implementing an interface and saying like, hey, maybe now I would like to have a JSON or a protobuf flag that contains a single configuration. Now, moving from a single command line world where you specify all your configuration on the command line to a world where stuff can change dynamically at runtime means that you probably want to check your values before you pass it into the thing that is using them. Usually, you do it on server initialization, right? That's great, except for the fact that if it changes under your feet, you basically are in a world of pain. So that's why the flagz library has a concept of validators. Whenever you change a value dynamically, be it on server initialization through the command line or later on using etcd, it will check this value and reject it if it's wrong. Additionally, if you want to run really, really reactive software, you can actually hook up a notifier to your code saying, for example, the config for my X, Y, and Z has changed. Please reload it and now use it to serve requests. Okay, so you're probably now like, what the hell? What is he talking about? So I'm going to give you a couple of code examples so that it's like pretty clear. I hope everyone here knows Java, I assume. Oh, no. All right. So this is a package, com example RPC client. And as usual in Java world, you have a factory of factories, but this time we only have a single factory. This is the class that will build your RPC client connection. Obviously, you would like to configure it somehow. And usually what you would do before, you would pass around a massive object that said like, and now I'm doing this. And here's 700 fields of how my RPC should behave. Instead, you can have a private static field that defines the behavior and adds a label to it. So in this case, we have RPC client max thread pool size that will control how many threads in a thread pool that does RPC execution will be spun up. Or for example, you can tweak the default RPC deadline that are being sent out of the server. And it's all fine and dandy, but how do you actually get this wired in? Well, in your Java main, you would just do flagz parse, and that's it. So flagz basically reflects through your whole code base, your whole class path, to discover those fields that are annotated with flag info and makes them available on the command line. So by just doing -- RPC client max thread pool size 15, we just tweaked something that would otherwise be a constant and would require you to recompile your whole code base. Now, you're probably like, yeah, but I didn't come here for like, static Java stuff. Like, where's the etcd gist? All right, cool. So basically, you use exactly the same thing, except for a little bit more of initialization code. So the same way that we initialized flags before, we now get a hold of the registry that is the pointer to all the flag fields that were discovered in the code base, and fire up an etcd flag field updater. Now, what the etcd flag z updater does is it goes to a path in etcd, as you can see, -- flag z etcd directory, and then assumes that every key under this directory is the configuration for your flag in your code base. Now, this is all fine and dandy, but it's probably not clear. So let me give you an example of how it works in a Spatial OS deployment. So you have a happy user. Well, I hope he's happy. But generally, he sends a flagz set request. So I would like to configure my stuff like this. Now, he sends it to an API server. And again, this is where the auth happens. And we're not going to discuss it right now, but it's pretty interesting in itself. And that API server, the only thing that it does is writes the appropriate key into etcd, and that's pretty much it. Like, this is the equivalent of me doing etcd ctl, set something greater. A-OK. Now, then you have the Spatial OS deployment starting up. And the runtime servers come up, and the first thing they do is they do a recursive read over etcd's directory to detect all the flag configuration that it should start up with. Now, that is all great, but where's the dynamic stuff? Well, after they read the initial configuration, they start watching that etcd tree for updates. And whenever a user does another flag set, that change automatically propagates to all your runtimes. Now, this is not atomic or synchronous because, like global synchrony doesn't happen, but it is fairly fast and fairly uniform across all your servers, and it makes experimentation really, really easy. And so most of you are like, yeah, you're talking about Java. I don't do Java anymore. Like, we're in like 2016, right? Like, who uses Java? So yeah, like, you probably, yeah, whatever, like, I'm not interested. So let me talk to you about the Spatial OS platform, like the thing that we built around the whole simulation stack. So we use, as I said before, we use CoreOS very heavily. Like, basically, everything that we run is run on CoreOS, and we are heavy etcd users. We run about, I think, 10 or 11 etcd clusters in whole, including our production and staging environments. We are very heavy users of Prometheus, and basically, again, run it to its limit. We also bought into the whole magic of gRPC fairly on. About half a year ago, we decided to re-architect our platform around gRPC and protobufs. And also, we use Go flags, because why not? Well, what is Go flags? I think everyone here who uses Go is fairly familiar with the standard flag library of Go. pflags is an extension of that allows you to specify the flags in a POSIX fashion, but also has a couple of really nice features. Like pflags is basically a drop-in replacement for flags. You just rename your import flag with import blah 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 GitHub blah 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 pflag, and you're good. Nothing needs to be changed. Everything is backwards compatible in terms of code. Now, what we did was we already had this, so we hijacked the whole pflags environment and decided to run with it by introducing one single shared flag set. If we have a monolithic repo that we build multiple services from, and basically we define a single flag set somewhere in our code base in some package that is used everywhere else. The normal static pflags that we had before, the normal things such as like what port should I be listening on, or what is the binding address for my server, that all works as it worked before, but we also introduced a concept of dynamic flags. The reason why we did that was, well, unfortunately, the standard flags are pointers in Go, and accessing pointers and changing them across multiple Go routine isn't thread safe. So we introduced basically the equivalence of the standard pflags flags, and that allow you to access those values from different threads and change them in atomic fashion. Now, since we carried over the knowledge from our Java stack to the Go stack, we also have custom value validators, because again, you can change your values dynamically, and you want to make sure that they're within a certain range, for example. And we want to be notified whenever, for example, we need to reload a piece of code based on the new configuration. Now, the other thing that this implementation comes with is a arbitrary typed JSON flag. So you can specify a flag as a JSON using an arbitrary struct that you have in your code. And as with the previous Java flags, this is also completely driven from etcd. Now, let me show you what the shared flag set is. So this is literally a bit of code from our repo. This is where we define the single set that is used throughout all of our services. And all of the flags and all the other packages that want to tweak their own behavior basically include this package and reference this set to instantiate their flags. This is an example of a usage of that shared flag set when combined with a dynamic string slice. So in this case, we tend to have a lot of code that we want to roll out new features, but we don't really know whether they're safe. So we basically have two implementations, the old one and the new one, in our code base, and use feature flags such as this to control whether this behavior should be enabled for the given request or not. In this case, we have API handler enabled features, which is a string slice, and by default, it has slow index in it. Now, somewhere in your code base, in some handler that we have a check whether this actually has fast index in its list of experiments. And if that's the case, well, it will just enable the new code path instead of using the old one. Now, the key thing here is that the get here is thread safe, so you can literally change it from etcd in the background while this is executing, and everything should be fine. Your Go race will be happy, which was one of the main reasons why we did this. Now, the typical initialization of shared flags and flagz from etcd is relatively straightforward. It's very much the same as the Java one, where you create a new watcher and tell it to use that shared flag set. You point it at an etcd client, and you say from which directory to read the config from. And again, you initialize stuff, and then you do start. Unfortunately, I don't know why it's cut off, but hey. Okay, now, since we started relying on this pretty heavily, we found out that, hey, running --help on a thing that is somewhere in a Docker container isn't really the best way of discovering your configuration. So that's why the flagz library comes with a built-in handler that allows you to list not only the dynamic flags, but also the statically configured ones, including help strings. This is literally the go-to place I go to a service and I want to see how it's configured. Okay, I just load this up and I see what has changed, how it was initialized, what are the help strings for those parameters, and is there something that I can do to modify its behavior. Now, you probably noticed the fact that there is a JSON flag here that allows you to basically say, okay, this is just a JSON blob. I'll show you an example of that in a second, but before that, it's worth pointing out that whenever you have a dynamic mechanism for changing the configuration of your servers, you would like to be able to be sure that all of your servers have exactly the same config file loaded. That's why we also have a monitoring stack that allows you to figure out what is the checksum of the current configuration of the server and compare it against different instances that you're running using some fancy Prometheus rules. Right. So you're probably thinking like, yeah, sure, but Go is fairly easy, it's all mostly stateless stuff, why would you even do that? And yeah, you're right. We could run our stuff by doing rolling restarts and just changing our configuration on the command line and be happy, except for the fact that we wouldn't be happy because we now know that it's possible to do stuff basically dynamically in real time across all of your servers. So let me give you a couple of examples of why this dynamic configuration is useful for us. So first of all, we have an experiment framework that allows you to basically say that what behavior should be enabled or disabled for a given RPC that is received by the platform, and then add it to the RPC headers as it propagates through the system, allowing us to have a consistent view of the behavior that a given mechanism should have for a given user. This same experiment framework allows us to basically dial in and out features of our code base. This is a step up from the previous dynamic flag that you saw, where we allowed you to enable or disable a new code path. We can now progressively roll out a given code path for 1% or 20% or 50% of the users that are interacting with our platform. The other case is rate limiting. If you have someone somewhere on a Jenkins server, oops, what happened here? Okay. If you have someone somewhere who wrote a bash script in a Jenkins server that uses your platform and just runs it in a loop and it just goes crazy, you're in trouble because you will not have a way of actually saying hey, please don't do that, because he probably won't know. This is not malicious. This is just omitting a comma somewhere that will mean that you are now pretty screwed. So it's fine to be able to change your rate limiting configuration when you're doing a rolling restart, but that A, may be slow, and B, it may cause you to lose capacity as you do it. Let's say that you want to restart them in batches of 2 and you have 6 servers. You now just lost 1/3 of your capacity to be able to just tweak a parameter of how many requests per user you want to allow. The other thing that we're doing is routing configuration for reverse proxy. As I said, we have a reverse proxy that allows you to basically peek into the bowels of the Spatial OS deployment runtime. If we want to add a new set of configuration or a new set of backends, we don't really want to take them down and risk the requests that are in flight to be terminated. We just want to enable a new backend for new incoming requests. With this, we can do it very easily. Now, this is an example of the rate limiting config that I talk about. Again, we use the shared flag set. This time we're using a dynamic JSON flag. And basically, the whole schema for it is embedded within a Go object as before. You have the instantiation of the config, and that is the default value, but it also provides the schema for the flag to know what fields are expected and how to pass it. That's pretty much it. The additional thing here is that, well, just passing the JSON isn't enough. You also want to check whether the stuff you got in the JSON is correct. So that's why we can attach a validator to the flag. And that's why we also want to change the rate limiting behavior of the library whenever this flag changes. So that is all fine and dandy. But as I told you, we are running about 11 etcd clusters. I think it's 10. We shut down one recently. I don't know. But it is pretty hard to keep all of those etcd keys for flags in sync across all of your servers. Well, that's why we're currently working on a pipeline that will do this in our name. So we decided to use JSONet for this. JSONet is, for people that used to work at Google, the BCL of the open source, which sounds bad, but actually is pretty cool. And what we do is we have the configuration in separate files, and then we compiled one single pb.json, which is a JSON file that actually has a protobuf schema backing it, and we just shove it into GitHub. Now, each of our clusters has a job, well, doesn't have it yet, but soon will, a config server that literally polls that GitHub, and whenever changes occur, it will reconcile the things that it got from GitHub into the etcd that we're running in that given cluster, and thus make all the platform clusters pick up the change pretty much as we did before. Right, so the cool thing here is that we open sourced both the Java and the Go implementations of the dynamic flags. So if you want to try them out or play around, each of those repos has a example, a small example that you can just run on your stack against your local etcd. Unfortunately, I'm running short on time, so the demo slide is being cut out. But if you're interested in working on something like this, find this man and talk to him. Just a obligatory plug that I had to put in. Sorry about that. Yeah, let's go to questions. If everyone has any questions.
The question from Small Enterprise World. Do you have any any stuff that connects flagz from Java to Spring, maybe to Spring values?
No. I mean, the way we built our service was very much framework free, and I think it would be possible to connect it somehow because this is literally just JVM code. But to be perfectly honest, I haven't looked into it. Would be a cool open source project in itself. So yeah.
Okay, thank you.
Oh no.
So I've seen you are using like prefixes for, I guess, avoiding name collisions. Is that the only line of defense, or what? Well, how do you detect them, and how do you deal with name collisions?
So yes, this is basically our way of resolving collisions across multiple flags in different parts of our code base. So far, we had reservations about going that route, but actually it works out pretty much okay. We haven't had any problems. It is a very much a YOLO approach, and better ways of structuring stuff would work, such as, for example, have cascades of flag sets. However, we haven't encountered a problem with it yet, so we didn't go with any changes towards that. Any more questions? Cool. Thank you very much.